Hello everyone. We'll wait for some time for other people to join.
Good afternoon, Subrat. Uh,
Hello, good afternoon. I'm waiting for some time for other people to join.
yeah.
If
I
it's
just,
okay, and I'll wait and then I'll start.
no problem. I was just saying hi. Yeah.
Hello. Is my screen visible?
Yeah,
Okay, so we'll start by solving assignment of week 6. So last week we solved for week 3, 4, and 5, I guess. And this week we'll start with the week 6. And so I'll be solving, like, if you have any doubt, you can stop me and ask. Or if you have any doubt apart from assignments, you can ask, like we can discuss. Uh,
yeah, no
if you
problem.
don't have any doubt, I can proceed with assignment 6.
Yeah, let's just start with assignment. If I have some doubt or I need some explanation, that would be, I will ask. Okay.
So before going to the week of 6 of assignment, I will briefly, like, tell what was in the week 5. So week 5 content was mostly on cost functions, classification cost functions, optimization techniques and learning rules, gradient descent learning rules. Those basic deep learning stuffs. And it also have this AZD and Adam learning rules, which is basically uh, deep learning, or you can say gradient descent learning rules. In the week 6, we'll formally start with convolutional neural networks, and this week started. The content started with how these CNNs are designed, and what are the basic building blocks of a CNN. So to briefly state, an image is we can represent an image as a tensor. So if it is one dimensional, it is called vector. If it is 2D, it is called a matrix. So when it is more than three-dimensional, it is called tensor. These are also called one-dimensional, two-dimensional tensors. So basically, tensor is a generalized term for any n-dimensional matrix or vector. So an image can be, like, viewed as a tensor, and an image contains three channels. One is red, then it is red green, and another is blue. So while evaluating an image, we can say that we can say that an image is a 3 cross n cross m tensor. So the reason I am stating what an image looks like is that earlier we used to work on ANNs. So earlier we used to work on ANNs. In ANN, what you do basically is that there is an input layer, and we basically feed this our input X to this, and it is propagated through other layers, and finally go to the output layer. But in case of a CNN, this is not the case. So the reason we started dealing with CNN is that so earlier what they used to do is that they used to flatten the image. If it is 3 cross m cross n, or let's say 3 cross 32 cross 32, then it will be flattened into a 32 cross 32 into 3 vector, which is around 3700 3072. And this input dimension will be this input dimension will be 3072. The problem with this method was NN was it was getting bigger and bigger, and as the image size went from 32 cross 32 to a full HD image, or 4K image, that went into millions. So we were sort of running out of parameters or memories to accommodate these images and perform learning. Also, so that this is reason number one, that this is reason number one, that the number of parameters were very high. So second reason was that these pixels here. So suppose there is a cat here. Sorry, the cat here. So these area matter. Like if you pick any area, this area matter, and this area should be near to each other to understand this image. Like when we see this all these things. But when we flatten this, what it do is that it takes these pixels and put it in one row like this, and then the green one also will come somewhere up, like after this. So this spatial relationship between the pixels is lost here. So first thing is that we need to reduce the number of parameters. Second thing is that we need to preserve the spatial positioning of the pixels, and to learn any pattern. So to resolve this issue, CNN come into play. So what CNN do is that the first goal is that it will share parameters. And sharing parameter mean that if I use the same parameter for learning different, like here I need different parameter for learning the different thing like W1, W2, and WN. But if I can use same W for these two, three things, then I'll have less number of parameter. That is called parameter sharing. And second thing is that I'm- second thing is that I need to look into this spatial thing. I need to look into the spatial thing. I need to preserve this spatial factor while learning my pattern. So to do so, I to do so, like second thing is uh, so to do so, what I need to do is that I need to suppose this is my image. I need to find another image which is smaller in size. So if it is m cross n, I need to find something m1 cross n1, and m1 n1 should be less than m and n. So this is goal one. I need to find a smaller representation of the same thing. Second thing is that my information should not be like I shouldn't be losing any information. Uh, I shouldn't be losing any information. I should have been like more careful while doing this, so that I can use less number of parameters, and I can also preserve the spatial arrangement. So to do so, we have certain operations. So first is convolution. Second is pooling. So these two operations, like we do these two operations alternatively to transform a big image to a small image, and to add any non-linearity, we use a activation function, and the commonly used activation function in case of these images and convolution pooling layer is ReLU. So these are like just basic things we need to remember before proceeding with any CNNs, and all the other CNNs are just special case of these like a special combination of these three things, and or a special use case it is solving, but the base things are this. uh, going into convolution, like I'll
Yeah, could you give some example of the convolution, like
yeah, yeah,
the
yeah,
operations that we do?
yeah, yeah.
Yeah.
2 minutes, 2 minutes. Yeah. So, so you want me to give example of convolution, right? Yeah. Hello.
Yes, like the mathematical operations we do basically as a conversion is a function, right? So yeah, that would be right.
So, this convolution was 1 second. So the convolution was introduced initially in the in domain of signal processing. Okay. So so what this said is that suppose there is a signal going like this, and they have another signal like this. So what they wanted to do is that they want to blend these two signals. This is signal and this is some uh, hit, and they want to blend these two signals, and they want to blend this signal into this signal. So the operation was S, this kind of star and this. So what they will do is that they will take this and apply to this part, take this and apply to this part, and they will do. And after this application, it will be transformed to some other waveform like this. So this was the case, and so this was the case earlier. Like we wanted to convolve our one thing around the other, and this will reduce like this will uh, extract some essential factors and reduce the size of the thing. And since like so what they did is that they took an image and they applied the same thing. Suppose the image is like this. So I am constructing a 9 by 9. Okay, so why should I do this? What I will do is that I will solve a question that is related to that. So, yeah. So question number 4. What will be the output of the following convolution operation? Uh, hmm. The following convolution operation with padding 1 1 and stride 2 3. So do you know what is padding and strides?
Uh,
What is-
I know the fundamental, but if I always get confused why we do padding and why we do stride. So that if you can, just like you really explained why we use CNN basically conceptually. So if you can just explain the concept behind why we do stride and why we do padding, that would be great. That would make things easier for me.
Okay. So the first I will explain like why. Let me okay see. So why stride and why padding and why so convolution is clear, right? So I guess
Yeah,
convolution.
understood. The basic concept, I got it.
So actually, these things are like so they assumed that image is so image is signal kind of thing. So and they try to do what they are doing in the signal processing to this. Like it's kind of not, it's not like that A was there and they just put convolution padding pulling everything at once. It was a branch coming from electrical engineering, and people are trying things that they learned in the electrical engineering in the images and sounds as well. So from there it developed, like they built an intuition, okay, this might work. And once it worked, they gave an explanation around it, like, okay, this, maybe this is the thing that's worked. So if you go deeper, like you will find all the signal processing and image processing stuffs, which is not something we care about today. Like if I want to learn like CNNs and all, so it's a long way. Like I mean, CNNs have been developed, and people don't really ask like why it is working. People just take the architecture and get the results, and all these things, layers, CNN layers, and are used in transformers and all. So people are like sort of forgetting how this was created in the first place. The example,
That's right.
yeah, the example is that, like, suppose for calculating a square root, okay, for calculating a square root in program, so you have to do the Newton method and iterative method to calculate the square root. But if I ask like any of the like people now, they won't be able to say how to code a square root. But if I just give you Python or C++, you can just use math.sqrt and just pass in a number.
Yeah,
Get I mean, so as the things
that's
have
right.
evolved, yeah, so we tend to less care how this started. But the starting point was that, like, a convolution operation, blending one signal to another. And second thing is that padding and stride. Okay, so while doing convolution operation, we need to care about padding and stride. um, so the explanation that I gave for convolution, I can give a similar explanation for Maxwell as well. But I would say that padding and stride is a is sort of a axiomatic definition. Like you cannot say why padding. So I can say why padding, but like you cannot say why it stride. So what stride mean is that, so I'll just let you know what this is, and then I will go about like why it is. I mean how to do that. So it is 1 1 2 1 uh, 1 1 1 2 1 3 4 5 0
6781.
6 7 8 1
Yeah, you can confirm, but yeah, I think
7 8 1. Okay. So so padding means that so suppose it is a dog. Okay, suppose it is a image of a dog, and you are adding convolution operation. So what how do you do convolution operation? That the filter, there will be a filter or kernel. So kernel was 1 1 2 3. So this is a smaller signal, 1 2 3, and we will take this and apply to this four block. Okay, one. So we'll multiply it. So it will be 1 1 4 in 3 into 2 6, and 4 into 3 12, like this. Then we'll add this. It will be 12 16 18 20. So the new image will be uh, it will be 20 here. Okay. So this is the convolution operation. We're just multiplying element wise, like element wise this to this, and then adding. Okay. So when I'll go here, shift here, so I'll take this one, then I will take this one.
so. Can I assume? I mean, these numbers here are the grayscale numbers, right? If we assume it's just a grayscale image, right?
Yes, yes,
We are
yes.
just
You have to assume
one
that.
channel. Okay. Wow.
So similarly, we'll get N2 and N3 by multiplying this and adding this, multiplying this and adding this. So then you will shift downwards and do the same thing for all these four numbers. Okay, but as and you will get N4, N5, and N6. So you have reduced a 3 cross 4 to a 2 cross 3. Okay. But the problem here is that if you see this 4 involved here, 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 and here. So the information that was captured with this pixel is now computed 4 times and is a part of this pixel, this pixel, this pixel, and this pixel, right? But if you look at this pixel, it is just a part of this one. Like if you see I mean, this 20 was coming from this one, and this 20 is like this 4 is contributing to these 4 numbers. So the information that is there in one pixel should be reflected in the smaller version of the image. Like this is the 3 cross 4 image, this is a 2 cross 3 image. So if this pixel containing some information, it should be evenly spread in this image. Like it should be also contributing to that portion of the image, or you can say this information should be kept should be part of as many pixel as we want, and it should be maximized. Like every pixel should get a chance to represent themselves in the smaller image, right? But if you see these corner pixels or all these top level pixels, they are getting less chance to sort of represent themselves in the smaller image. So that's why what we did is that to facilitate so or to involve all these guys more in the next image, we do padding. So how padding is done, that we basically and we do what to do is that we add a layer around it. Okay, we do this, and we add 0. This is called 0 padding. We're sort of adding black borders to our image. So this is called 0 padding. You can also do one padding, like it will be white border around the image, but typically we do black padding because it is like you don't have any information, so it doesn't contribute to much. Like it doesn't like sort of disturb the content of the image. So if the padding is 1, we add just one set of 0. Here the padding is 1 1, like we need to add as one row and one column. Okay, so now if I take this, here 1 will be involved, here also one will be, this one will be involved, here also this one will be involved, and here also this one will be involved. So this is the thing. Okay,
Yeah, understood it.
so
Thank you. Yeah.
this is the case of padding. And what is stride? So stride is that how stride is also similar thing. How well, so how like how much do you want to save in an image? So suppose if the image is very small, you want to save much of the information. If the image is like very large, so you just want to reduce it. You don't want to save much of information, so you can use a larger stride. So stride is something that, suppose initially you will do, so your filter is 4 cross 4, so you just took this 4 cross 4 cross 4. If the stride is 1 for the next operation, so you will do from here. Okay, but if the stride is 2, so you will skip 1 row and 2 row, then you will start from here. If you do this, this one will not be involved here. So here it will be involved here and here, not here and not here. So here earlier it was getting involved 4 times. Now it is getting involved 2 times. So the number of times it is getting involved is reducing. Hence, the information that we are capturing of this pixel to or transferring this pixel to the next smaller image is low. So if the information in your image is like it is vast. Like if it is a thousand cross thousand image, so suppose there is a cat, or so there is, say there is a fish. If it is thousand cross thousand image, if you skip this bit, it won't matter because it's just a fish. Like you capture this part, you can easily assume that okay, this will be straight line. But if it is
And
a
we also assume that that the approximate pixels have the same characteristics, right? So why we connect we can just keep it. That's what the logic, right? Or thinking that that's why we try to do strides and skip some pixels, something like that, right?
yes, yes, yes. But it's a trade-off, right? How much you want to skip? You cannot just like take stride
Yeah,
one.
so it's just trial and error, right? That's why
It's a trial and
experimentation.
error. It's a trial.
Yeah,
Like everything here in this CNN is a trial and error. They
yeah,
just so ResNet and GoogleNet, all these things, if you see, like are developed by a corporate, not some like or some big labs, not by some normal people, because you need resources to train these and give results as fast
yeah.
as possible.
That's
So
right.
they tried different combination and they sort of tried to build. So they got an intuition, they trained a model, and they sort of tried to build a theory or some math around it. It's not like that they proved something, then they do the experiment. So what they
Yeah.
do is that they experimented and they tried to build a math around it. So this is the stride operation, kernel stride. So once, so this is done, right? So now I can like solve this question. So this is the input size, padding is 1 1, and stride is 2 3. Stride is 2 3 means in this direction the stride is 2, in this direction the stride is 3. So in this direction the stride is 2, in this direction the stride is 3. Okay, so it is 1, right? So if I multiply 1 1 6 12, sorry, not 1 1 6 12, 1 1 2 3 to this block, it will be 3. I'm getting 3. Then the stride is 2. So I shouldn't be starting from here, I should be starting from here. So if I multiply this, it will be, let me write it here again. 1 1 2 3. It will be 0, it will be 2 6 8 8. If I do the same thing here, it will be only 2. And if I do, and the stride here is 3, like I am standing here. So one stride skipping this, two strides skipping this, three strides skipping this. So I should only be doing this one. So we are just skipping the entire row here, I guess. I guess. Yeah, we're skipping the entire row. Then if I multiply this block with this, we'll get 1 into 6, 6, and others will be 0. Then so, yeah, multiply this with this, it will be 7 plus 8, 15. And this block with this, it will be 1 only because 3 will be 0 and this is 1. So this will be the size. So we had earlier 3 cross 4. Now we have 2 cross 3. This would be the answer, 382 615 1. 38 382 615 D. Yeah. So
Yeah,
this is
got it.
the convolution operation that is there. Like you can set different strides and all, but currently, like from a practical point of view, we are not supposed to design like, so there are two way. Like one is that you learn a thing from a research perspective, so why this happened, and so what is the trade-off between like this stride and all. So if I like change the stride, if the accuracy is increasing or decreasing or all sort of things, so you can explore that way, like, and it will be, so there is not much of a math here. Like you cannot find any bounds written for this. Like you must have saw that there is bounds on number of samples and the accuracy. Like so you, for a certain reaching certain level of accuracy, you must have this number of samples, or there is bounds, or there is relationship between the number of samples and the dimension of samples. So it's not like that you have 1,000 dimensional feature and you have only 100 features. You cannot learn anything out of that. So it has to be larger than that to learning anything meaningful. But there is no bound. If you see, there is no bound in this image, like strides. If you change the slide, the accuracy will drop. I mean, it might drop, it might not drop, depend upon the data set and all. It's all part of the experiment. If you're learning this as a tool, so you have to do the experiment and see. But basic things what people do is that they just take the existing architecture and try to modify there so that they don't have to start from the scratch. So this is about the convolution operation. Second thing is the pooling, right? So convolution, after convolution, there is pooling. So convolution is kind of so convolution we're sort of uh, blending information and using those information once again. But in pooling, basically, let me do another block. So pooling has two or three types: max pooling, mean pooling, and average pooling. So what they do is that they just look into if the pooling dimension is 2 × 2, they'll look into these four elements and they'll pick the highest one. This is called max pooling. Highest one, like if it is 1, 2, 4, 0, 4 will be picked, and this three will not be picked for the next layer. So what they are doing is that they are not.
So can we say in logical way it would be really I would say conceptual, not really mathematical way of saying, but we can just say when we are doing max pooling, we are just taking the pixel which has highest intensity, basically
Yes,
something which is more representative of that section of image, right?
yes, yes.
Uh, yeah.
Yeah, we can take average, but max pooling is something we use generally. So, so this is the like argument that we are posing that okay, so these from this area, I want someone like who is representing this area much, not others. Like I can ignore others. So that sort of thing. This is pulling.
Uh,
So what we do is that generally we club these things. So conf plus pooling plus there is a ReLU there. So again, this thing con plus pool plus ReLU, same thing. And we do this until we get a image which is smaller in size. And there must be some dimension associated with it. So we do this till we get an image which is very small, very smaller in size, and we can sort of make it flatten and make a fully connected layer out of it. And this fully connected layer, then there will be ANN, and at the end there will be classification layer. So this is the idea, and people have done different things for different architecture, but we'll not discuss that in the lecture. I guess it is clearly mentioned. So we'll start solving the assignment. Coming to the question number 1, what is the range of ReLU, P-ReLU, and R-ReLU functions respectively when provided with an input range minus input infinity? So we are sort of so this is our input image, and we sort of so we have an input image. So 3 cross m cross n. We applied convolutional layer, then max pool layer, then we apply activation. We apply activation to provide the non-linearity, and after we got the output from here, we repeat the same thing here as well. So I have discussed convolution. I have discussed Maxwell. The time is now to discuss the activation function. The activation function is to provide non-linearity in our architecture. So the one of the primary things that we use as activation function is ReLU. ReLU. So the structure of ReLU is that structure of ReLU is max between 0 and x. So if a function is like this, and if I pass it into a ReLU, it will be like this. So for each point, it will check if x is greater than 0. If yes, then it will be x. If no, it will be 0. Here it is 0. So this will be 0 here. Similarly, these points will be 0. So the activation function looks like this. 1 second. So this is the shape of the ReLU. I guess this plot, I mean, this is the function max between 0 and x. But yeah, if the input is so this curve doesn't represent this clearly, I guess. Like if the input is something less than 0, it will be 0. The output will be 0. If the input is something greater than 0, the output will be x itself. Here the input is, yeah, so input is, yeah, this should be like this, right? Oh, yeah. So this is the step of the value, like if the input is less than x less than 0, it will be 0. And if the input is greater than 0, it will be x. But I'm not sure. So for this function, if the curve should be this or this, because if it is like this, yeah. So the value of a function, right? The value of sin x. It's not showing.
I think by definition, anything goes which is negative, it goes to zero,
Zero.
right?
Yeah, zero.
And basically whatever the value we have, it just prints that. So I think you're right here. This one should be the activation function values, I
Yeah, but
guess.
so yeah, so it's if it is x, if it is x, yeah, this shouldn't be the, I mean, this shouldn't be the correct curve because so here I'm plotting x and y. So it's sort of like I can say I'm plotting sin x. So I cannot pass sin x to ReLU, right?
Yeah, that's
I
the
mean, I
point.
should pass
Yes.
x to ReLU. And,
Yes.
so it's
Hmm.
like if you traverse like from minus infinity to infinity. So so the question, like coming to the question, it will be like I'm just using ReLU in a different way. Like if I pass sin x or this function of x, then this might be the output. But here it is saying that if the range of input is minus infinity to infinity, so now the x is varying from minus infinity to infinity. So this entire range. So this is x and y is itself is ReLU of x. So here the y was some f of x. So that's why I was getting confused. So here it will be the x and y will be ReLU of x. So now like if my x is negative, it will be 0. X is positive, it will be x. So this is the curve that I will get. So I was looking for this curve, but I was not sure. So here I am not passing x to ReLU. I am passing this function to ReLU. So here I am plotting ReLU of some f1 of x. So I was plotting this. So that's why I was getting confused. So it's asking if my x varies from minus infinity to infinity, how the ReLU will vary. The ReLU is y. My y will lower bound at zero and upper bound at infinity. So for ReLU minus infinity to infinity will get converted to 0 to infinity. And there are two other methods. One is PReLU and second one is ReLU. So PLU is peaky ReLU and the curve goes like this. It's not really zero, but round it, and ReLU is randomized ReLU, and its curve goes like this. Like we take peaky ReLU and we add some random noise and transformation around it so that it looks like this. And if you see, so these are kind of making a some angle theta here, and this is not, they are not parallel lines, so it will of course go to in minus infinity like this. If you go to minus infinity, hence if you range x from in minus infinity to infinity, it will go from minus infinity to infinity. So the answer is D in this case. Yeah, this bracket will be open, close bracket, open bracket, sorry, close bracket. Yeah. This open bracket can be shown this or like this, like this, like this. Yeah. So question number 2, which of the following deep neural network layers are not trainable during training? Fully connected is trainable, and convolution is also trainable. Why convolution is trainable? Because we are using a kernel. So this kernel, so this 1123 is a kernel, and so this kernel is something we called filters, or we also call it kernels. So these filters are weights W1, W2, W3, and W4. Initially, we don't have this value. We have just random 4 value. Then we convolve it around the image and get a smaller image, which will be passed to the fully counted layer and get the output. And while doing the loss and updating the weights and using backpropagation, we want that give me those weights. If I will convolve those weights in the image, it will give me a better representation of the image in the smaller layer so that it will boost my classification. So here sort of we want these weights. So we pass random weights and go to the end layer and we do the backpropagation, and we want these weights to be that efficient, such that should be in the state such that if I convolve this weight around this image and get a get a output, and I keep on doing this the same thing, I'll get a representation which will help me classifying the image better. So before proceeding, let's let you know one thing. So since this what earlier it was they are doing is that I don't know if you know this or not. Suppose this is a grayscale image, okay, and I have a filter here. So filter F1. So filter here F1 is some, let's say, edge detector, and they used to design this. They used to handcraft this feature one, such that so they used to like put -1 1 1 -1 or something like this, such that this will extract me features, edge features, and they will use another filter for curves. Okay, F2 for curves, and they will use another feature, let's say F3 for blurriness and all these things. So they sort of designed different filters for different things, and they used to convolve these features in the entire image, then convolve this one, then convolve this one, and they used to, like, if I convolve this one, I'll get image one, right? And if I convolve this one, I'll get another image. Okay, I get another image here. Okay. So if you see, if you go to the if you see edge detector, you can see images like this. So if you pass that edge detector filter, you'll get edges like this, right? And if you get blurriness filter, it will blur the entire image, or you can find curves around the image. So what they are doing is that they are getting these images, and they were doing machine learning on this. So what CNN did is that they said that no, we don't need to specify that edges or curves or blurring something, sharpening something will give us features which are important for the classification. We don't want that. We just want an machine learning model to learn what features we should apply, such that we'll get very better classification results. So that's why instead of defining this -1 1 1 and -1, they just put weights W1 W2 W3 and W4. Okay, and these weights they convert, so this will be random, and this will not give me a image. So if I convolve this around this image, it will not give me a image with edges. It will not give. It will give some random set. Okay, and if I train it, if I do multiple iteration, so these filters, like if I just apply 10 features or 20 filters, they will understand that, okay, I need to filter out something which is important for classification, because they have to maximize the classification value, or they want to minimize the loss. To minimize the loss, they will come up with weights which will like extract features and extract images which is very meaningful, and they just don't want any edges or curves. They might generate something some combination of edges and curves which we human cannot design a filter for. So they kind of learning the pattern, and they might have got any patterns which doesn't define themselves, define them in edges and curves. This might, like, they might got like other things as well, which we human cannot like design filter for. So they do that, and they get all these images, and they club all these images like this. So if suppose there are like 20 features, I'll get a image output of like this. So this is the output of convolution, fast convolution layer here. Then I will apply max pool. So input image was 3 m cross n. After adding convolution, my output will be some. So there was 3 m cross n. It was 3 m cross n. So I add, so if the channel number of channel is 3, my filter will also have 3 channels. So it will have 3 2 cross 2. Okay. So I did the filter around this image, and I got all these things. Like, so so if I got 10 filters, let's say 10 filters, so I'll get 10 images here. So if I join all these things, I'll get an image of 10 into m1 into n1. And this m1 and n1 will be smaller than m1 n. Then I'll do max pooling. This pooling will not reduce the number of channels. It will just reduce the m1 n. So I'll get 10 into yeah, 10, I guess. Yeah, I'll get 10 into m2 cross n2, and here m2 cross n2 will be smaller than this m1 cross m1 n1, and then I'll apply relu. Relu will not change anything, it will just transform these things. Then so after this thing, let's say my final output is for this layer is 10 cross m2 cross n2. Okay. So then I will again apply convolution layer. Okay. And in this convolution layer, the filter size will now change. Like if I am using 2 cross 2 convolution, the filter size will be 10 cross 2 cross 2. It will be like this. So there is a common misconception that it should be 2 cross 2, but it internally picks 10 because the dimension of the channel size has changed to 10 now. And if I use, let's say, 20 filter, I'll get 20 different images out of this by applying this. Then my image size will be 20 cross n3 cross n3, and it will go on. Like this m and n value will keep on decreasing, and this filter size, the channel size will keep on increasing. At the end, we'll be getting a long kind of image like this with many number of channels, and its size will reduce to let's say 10 or 20 kind of thing.
Yeah, so we can just say that the big image that we have is basically divided into more smaller image, but more number of images,
Number of
kind of uh, kind of extracting some information in each layer, you can say, right?
yes, yes.
Very good explanation. Thank you.
Yeah, so common misconception is that if the image is if the image is 3 cross say 1000 cross 1000, 3 into 1000 cross 1000, so what is the size of filter that we need to apply? Like so initially we are hand designing, so now we said okay, let's assume some filter w, and we want to learn this filter. Like so what features that is important, you learn and give it to me. So the filter size will be 3 cross 1000 cross 1000, not 1000 cross 1000 only. So earlier people when used to they used to show that okay, this is the, so people used to show this like this. Okay, that's where the misconception comes. But
Yeah.
originally it is like this. Like there is a image, and it will have dimension 2 and it will have dimension 3, and I'll have a filter just looking like this, dimension 2 and dimension 3. I'll take this entire thing and apply it to this entire block. Entire block. Okay. So entire block will be applied by this. Okay. And this will give me one value. So after like if you apply everything, so if you apply again here, like in here, you'll get another value. Let's say n2. Let's say name it as n1, and this is n2. Okay. And and the similarly you'll get n3 and n4, and you'll get an image n1 n2 n3 and n4. And if you, this is for filter 1, is do same for filter 2, you'll get another. In the for filter 3, get another. It same do for filter number 10, you'll get another image. So this will be your output image. So now the image will be, say, 10 2 cross 2. So this is like very small, but it is like 10 cross 2 cross 2. It might be 10 cross, say,
Yeah.
200 cross 200, like this.
Perfect. Thank you. Thank you, Amit. This was like mind blowing for me. I couldn't understand it before. You kind of cleared. This is basically what you need to know to apply using PyTorch or whatever
Yeah,
you're
I
using,
don't, but I
right?
can show you like how you can.
Yeah, that would be really great. Yeah.
So this is
Before that, is it okay if we can just briefly discuss how back propagation of forward and back propagation is working here?
the
If we
convolution layer.
can, yeah.
So it's kind of complex. Like so for ANN, you know.
Yeah, I know, of course.
ANN, like
And yeah,
so here you can just say that, like if I just go on writing the entire differential and all these things, it will be. I also need to remember all these things because those things need practice. And if someone is like teaching every day, he must be remembering this. But I would say that suppose it is W. Okay. So suppose let's say it is a filter and this W has W1, W2, W3, and W4. Okay. Let's say W. Okay. And so let's say I'm applying this W to an image I, and I'm getting some new image I dash. Okay. So what I can say that, and this I dash is getting fully connected layer, and let's say give me Y. Okay. I can say that this Y and Y hat, let's say I hat, this Y hat is a function of W, right? I mean, what I'm basically doing is that I am taking I and I'm adding a convolution operation to W, and I'm getting ideas. So this is basically ideas. And then I'm doing some fully connected layer, FC, FC. So what I'm trying to say is that FCI convolution W equals to Y hat. So this is so this is sort of saying that uh, if this is a function of y dash, I can take d of y hat with respect to d of w, right? Or you can say gradient of y hat with respect to w. So this is the way we write. Um, uh, s- so when so if some y is a function of f of x, I can take gradient of y with respect to x, right? And how exactly I am doing this, like it will, like you have to go through the this operation. So if you expand this operation, there is some integrals of I and then w dw. So you have to write that, and so you have to actually you have to write y dash in terms of this entire thing in w.
right. Mhm.
Then you have to take a derivative of that using w, and the value you got, it will be gradient of y with respect to w, and
Mhm.
you have to do this y w whole minus lambda, which is learning rate, into gradient of w.
Same as the back, like normal.
Same thing. We're just assuming that there is a w, and it is
Mhm. Yeah,
uh,
our weight factors is basically our filters, basically.
I can
Right.
share with you like one some resource where you can just
Yeah,
see
that would
derivation
be. Yeah, that would be
using,
great.
but yeah. So basically, like going to derivation is not also in the course. I don't think they have went into the derivation of all these things. Derivation
Yeah.
is needed, but not that much. Like
Yeah, understood. I just wanted to know what are the weights. So basically, filters are the weights on which we initialize
you
it
have to
and
write all those functions and then
training. Yeah.
find the derivative, and I mean, it's sort
Mhm.
of algebra.
Yeah.
Understanding sort of thing is, if you remember, like if you know the that like the ANN back propagation equations, then it's the same thing, but you have to
Simple.
do algebra here. So for RNN,
Yeah.
you have to do Taylor series approximation of the same thing and then do. So it's basically like I'm trying to find a gradient of this with respect to this, but this function
Mhm.
is not that. I mean, it is ill posed or something. So I cannot do this function directly. I have to approximate this function with something continuous or differentiable. So yeah, approximate this and approximate that. So all these derivation stuffs are all the math stuffs. What I do is that, like, just intuition is clear and I can just call the backpropagation function in the PyTorch. So
That's right.
it is the way, like, I'm currently preparing. Also, this course is preparing that way.
Yeah.
Oh, so this one was convolution operation and all these things. And what I was discussing, which of the following different network are not trainable during training? So max pooling is not trainable because max pooling is something, you can say, maximum of x. So maximum of x is not differentiable function. So we cannot like flow gradient through this. So
Yes.
there is no parameter here also. That's why we cannot train this. But convolution and fully connected layer can be trained. Question number 3, what will be the size of the output tensor obtained from a convolution layer with a single filter of dimension 3, channels, 11 into 11 spatial span operating on RGB image of 3 cross 100 cross 100 for padding. 2 cross 3 padding is used and stride is used of 3 cross 1. So there is a formula actually. If you like, if you sort of work through it, you will get the answer directly. I will discuss that. Give me, so I guess, what is the time? It's Shruti is there. So it's 5:15 already. So let me take a 5 minutes break. Like,
Yeah.
what's
Now we'll meet at
5:20?
5:20.
5:20.
Okay. Cool.
Hello.
Yeah, hi.
Got a bit late.
It's okay.
So there is a formula, I guess, for this. Uh, 1 second. Yeah. So here's the formula. Like, so if the image size is m cross n, okay, and sorry, the image size is yeah, if the image size is m cross n, and image size is m cross n, and the kernel size is width cross height, and padding is p width into p height. This will be height, and stride is s width into s height. Then the output of the image, the output of the image size will be x cross y, and will be the size. So if the intuition behind this is that let's say the image is m cross n. So m, let's say, is 4, right? It's just 4. If I use a filter of 2 cross 2, I'll get this 1, then 2, then 3. So basically, I am subtracting. So if let's say padding is 0 and stride is let's say 1, so this formula will be m minus w plus 1, right? So earlier it was 4 and the stride size was 2. So 4 minus 2 plus 1, it will be 3, because I'll get one number from here, one number from here, and one number from here. So I'll get 3 numbers, n1, n2, and n3. This was the case. If I have added a padding, let's say, yeah, let's say I have added a padding of 1, I will add in this side and in this side. So I am adding 1, but I am adding in the two sides. So this will be 2 into padding, which is this one, 2 into PW. And since the padding is added, so now my image size will be m plus 2 PW, which is, and then I'll subtract my h from here. So this is the case. And now I will be getting one number from here, one from here, one from here, one from here, one from here. So 3 plus 2p, 2 into 1, which will be 2 into 1, it will be 5. If I'm adding another stride as well, if I'm adding stride, so here it is stride of 1, like I am getting a number from this 4, then I'm getting a number from this 4. But if a stride is 2, I'll be getting now from this 4, then I'll be getting doing for this 4, I'll skip this 4. I'll directly do this 4. So I'm skipping one. So for this, for skipping, I'm dividing it. So if the stride is 2, I'll be dividing it by 2. Because now it will be this 4, then this 4, then this 4. It will be 3. Okay. So that's why like I'm dividing it again. So this is the entire formula. Height or width minus height or width plus 2 into padding into height or width by stride of the width plus 1. Now I'll just copy the value that is there in the question. So this is the value, and so there is given a number of channels. C equals to 3 here, and the stride will be 3 here. But you can see that this operation is irrelevant, like not irrelevant, like independent of these channels, because it will be applied across the channel 11 cross 11 into 3. So it won't matter. Calculating the value, it will be 100 minus 11 plus 2 into 2 plus 1, which is 89 plus 4 plus 1, it is 94. Similarly, 100 minus 11 plus 3 into 3 plus 1, it will be 89 plus 9 plus 1, 99, 94, 90. Okay. Oh, the stride is there. Sorry, I forgot to divide the stride. So let's just divide by 3 and divide by 1. And mhm, padding is okay. Yeah. So did a little bit of mistake here. Sorry. It should be 2, and here let me add this division by SW is 3 by 1. It will be uh, it will be 90. 89 plus 4 is 93. 93 by 2 by 3, and it will be 96, 90, 95 by 1, and plus 1 plus 93 by 3 is 31. So 31 plus 1 is 32. 31 plus 1 is 32. 96. 32, 96. Yeah, D is the answer. So my voice is audible, right? I was solving.
Yeah, all good.
That question is clear, right? So
It is clear.
basically, as you saw that the channel length, like channel width, doesn't matter much. I mean, you have to get same channel length filter, so it won't matter.
Yeah.
Hmm. Which of the following is true about LeanNet 5? Hmm. So LeanNet 5 is just a architecture. You can just see like what is the correct dimension and all this stuff. So yeah, so there is nothing to explain here. Which of the activation function does not have unity gradient for a positive input? Yeah, so this I discussed. Unity gradient means the gradient is 1 for the when x is greater than 0. If x is greater than 0, ReLU will be like this, and PReLU will also be like this, and ReLU will also be like this. It will always be x, because when x is greater than 0, ReLU, PReLU, and ReLU is x. So if you take differential of x with respect to x, it will be 1, and its gradient will be 1. So I can say that, but for sigmoid, the function is like this. Function is uh, like this. So the gradient is not 1, like here it is 0 almost. So the answer will be sigmoid. For sigmoid, the gradient is not unity when the input is positive.
Yeah.
State whether the following statement is true or false. Max pooling layer equips convolutional neural network to be locally invariant rotation. Uh, is convolutional locally invariant rotation? No, I guess like if you rotate, so what it is saying is that uh, what it is saying is that if there is an image and I apply max pooling MP, let's say, and I'm getting another image, and if I rotate this image by some degree theta, and I get another image, and if I do max pooling, I'll be getting an image which is similar to this one, which is false, because like if I rotate it by 90-degree, the max pooling value that I will get here, the max pooling value that I got already here will be different, because it will take the maximum of it, and it will be variant to rotation. So it will vary when you rotate the image. It is not rotation invariant. Same way, what is the size of output of a max pooling layer with filter size this, padding this, and stride this for an input size of 28 into 256, 258, 255, and 255. So, so this is similar. I guess like I just need to apply the formula here. So I won't be like solving this. So if I just directly say that it will be 255 minus 255 minus 5, 250, then plus 2 into 1 padding. So it is 2. So 252 by 3. 252 by 3 is 252 by 3. 3 into 6, 6. 3 into 8, 24. 15 into 5, 85. So
Mm-hmm.
this will be 85. So 85, and for second one, it will be 255 minus 5 is 50, and plus 4, 254, then by 2, by 1, because stride is there, by 1, 254, then again plus 1 is for this one, this plus 1. So it
Mm-hmm.
255 again. So the answer will be 85, 255. The channel length. So here, see, so here what they are doing is that here the filter size is 5 plus 5. I can use a filter size of 28 into 5 plus 5 to get like, so usually what they will do is that they will use a filter size of 28 plus 20, 28 5 plus 5, like this, 28 5 and 5.
Mm-hmm.
it will reduce the image to a one-dimensional image of this output 85. Sorry, 85 cross 255. This will do that. But if I say that, okay, no, I don't need to apply this 28 channel filter, I'll just apply one filter for each layer of my image. My image is 28 channel image. So if I'll just apply one for each layer, I will get 28 cross 85 to cross 255 size image. But usually what they do is that they took 28 channel filter of 5 plus 5 length, and they take around, let's say, 32 ones, and you will get 32 85 cross 255 images, and they will you will club all these things and you get another image of channel 32. So this is the actual way of doing, but since it is specified specifically that it is 5 plus 5, so it will be like this.
Yeah, got it.
The max pooling in convolutional network performs an operation which is equivalent to which of the following morphological operation which is commonly employed in image processing. Um, it will be dilation. The answer is dilation. Because like max pooling, yeah, but it should be erosion. But what I saw is that they gave the explanation for dilation. Um, so dilation is something like you pick the border and add pixels around it, and erosion is that you pick the border and remove pixel around it. So max pooling seems like removing something because we are reducing our image.
Image.
I'm not sure like what the exact thing like it corresponds in the image processing era. Yeah. So this assignment is over, I guess. So I will.
Yeah.
So I'll not go to the assignment 7 because I don't think there will be much time today. But I will now try to code that up, code the convolutional neural network that I tried to discuss here.
Yeah, that
In
would
week
be.
6, you will see that there will be some simple CNNs, and week 7, there are some specific CNNs like which are designed using some intuition by some companies. And week 8 is also some that those networks I can cover the assignment of week 7 and 8 combinedly because I had to discuss some fundamentals of CNN, so that's why I
Mhm.
couldn't cover.
So next week we'll have same classes, same time, right? Or we have to just one class, one doubt clearing session, 1 week, right?
Yes, yes,
Okay, same time next week. No, right?
yes, yes.
Okay, great.
Yeah. So yeah. So this was yeah. This is done. So I'll go to code and see if I can stop share and share it again. Yeah. My screen is visible, right? Right.
Yeah, I can see.
Yeah. From 28, I'll start. Uh, So this is basic importing all the libraries. Define the network architecture. So I'll do this now, like how this is. Uh, okay, let me share the entire screen. Share screen desktop one. Yeah. So how this is like sort of related to these things that I discussed here. I'll discuss that now. Filter size is, yeah. So here we are defining the network name here, and we're sort of yeah. So first is convolutional layer. Okay. So here we'll define the layers, and here we will define how the input, when a given input X is defined, how we are going to forward pass it, how we are going to process it step by step and pass the value from one layer to another. Once we define that, we'll define the network itself. And once the define is network is defined, and how the X is going to be flow from the input to the output is defined, you can just do loss dot backward. It will just do the backward propagation for us. We don't need to do it. So first thing is forward pass, then calculating the loss, backward pass, and updating the weights. So out of these four things, we need to define the forward pass, and we need to define the loss calculation. So these two things we need to define. Once this is done, backward pass and updation of weight, it's just two line of code. So yeah. uh so starting with LeNet. So I'm defining a convolutional layer. So convolutional layer is defined by from this torch.nn for on your network. I'm getting this con2D. So I'm getting a two-dimensional convolutional layer, and for MNIST it is two-dimensional because it is grayscale. For Cipher 10 it should be three-dimensional, and yeah. So here the first thing is that the first thing should be let me see like definition, like what's your quantity. So it should be filter size. Yes. Yeah, the in channels. What is the number of channel that I'm getting from my input? It should be one because I'm getting a I'm doing it with MNIST. So assuming the grayscale image, the channel size should be one. And second is out channel. So how what is the output of the channel that I want? If I'm adding is it at six, I'll get a six channel well output, and the kernel size is fixed as five. So the size of the filter will be five. So if I just define it in the image, it will
So
be
here, when we say size of filter is 5, it's just it's
5
not
plus
like a, yeah, it's just a vector then.
it is a 5 plus 5
Oh, it's 5 by 5. It's like they just say 5, it's just a square. So okay.
yeah, yeah, it's a 5 plus 5 filter, and we want the input image is here. Let's say here the input image, let's just consider MNIST. It will be 28 plus 28, and the channel is 1 now. Okay, and we have a 5 plus 5 filter. The in channel is 1, the out channel is 6. So what is this out channel? This out channel is that, so to get a, so if I take this filter and apply this throughout the image, I'll get an image of size. Let's just calculate 28 minus 5 plus 2 into padding, which is 0, by the stride is, let's say, 1. Okay, if by default the stride is 1, so I'll get a 23 plus 23 image, right? The output will be 23 plus 23 image. But I need, so it should be 1 into 23 plus 1 or 23. But I need a 6 channel input output. So what I will do is that I will, so this is filter 1. So I will define 5 more filter: F2, F3, F4, F5, F6. So for from this 5 filter, I will get a 23 plus 23 image. Then I'll club all these things. Then I'll get a image of 23 into 6. I mean 6 into 23 and 23. So this is the plan. So here, when I'm specifying, I need a channel size of 6, output channel of 6. I'm expecting an image of size 6. And I am expecting that by convolving my 5 plus 5 kernel in the image. So the code will understand that, okay, I need to create 6 filters of this size and go forward with it. Okay. So this is the code number 1, line number 1. So similarly, I am doing a max pull 2D. So it's a 2D pooling, and the kernel size is 2 and stride is 2. Since it is a 2D pooling, what it will do is that it will take this image and it will pool. So there's a pooling. So let's say it is a max pull filter. It will be applied to the channel number 1, and I'll get another image of some smaller size. Then I'll again apply to channel number 2, 3, 4, 5, 6, and I'll similarly get a image of say M into M into same channel 6. So the channel number of channel will not be changed here. It will be 6. When I'll apply again a convolutional layer, you can see the now the in yeah, now the in channel is 6 now, because I have an image of 6 cross M now. And so that, and I need a output of 16 channel. So this will be like, so since I need a 16 channel and I am using a kernel size of 5, so my the filters that this code will generate in the background will have size of 16 into 5 into 5. So this will give me one image. Similarly, 16, sorry, it will have, it will have 6 cross 5 cross 5, because I'm convolving around this image, and there will be 16 such images. There will be 16 such filters, and each one will give me one image, and the output I will get an image like this, where the size will be some M1 cross M1, and it will be 16, because I have I got 16 the 16 filters out of it. So 16 and kernel size is 5. Similarly, max pull again. And after all these things, if I flatten that, it will be of size 400. So you have to calculate this actually. So after all these layers, what will be the size? You have to calculate this and put it here, so that fully connected layer can be done easily. So 400, then 120, then 120, then 84, 84, then 10. So how the forward is defined? It is defined like, first I pass the convolution operation to X, then I do a ReLU, then I do a pull, then convolution to ReLU, pull, then this is the code for flattening. What I do is that I flatten this 16 into 5 plus 5 minus 1. Then this flattened thing is passed to my fully connected layer FC1, FC2, FC3, and getting the output now. I'll just run this block, and I'll just print the net. The network is like looking like this. And let's just take this is the random input vector. So input tensor, we'll say tensor. So here the batch size is 1. So the tensor, the image that we are passing should have 4 dimensions. One is batch size, second is channel, third is the height, fourth is the width. Here the batch size is 1, because we are just passing one image. Then we're just passing one channel and 32 cross 32. Let's just run this. And yeah, so when we do a object of this, and when we pass anything to the object, it will be executed using this forward function, and it will be forward pass. So I'm getting this. The forward function is like have these print statements, So 32 cross 32 is getting reduced to 6 channel, 28 cross 28. Then the channel is not changing, it is still 6, but I'm getting 14 cross 14. Again, the convolution layer is changing the channel to 16, getting 10 cross 10. Then the channel is not changing, the image is reduced to 5 cross 5. It is 1, 400, 1, 120, then 184, 110. Okay. Let me just check if 28 is a valid 28 should be the valid should be correct, because see the inputs image is 32 and the kernel size is 5, and there is no padding. The stride is 1 plus 1. It is 32 minus 527 plus 1 equals to 28. See, so it is giving a correct output. Similarly, other things can be derived. And trainable parameters. What is the number of trainable parameters? You can see the number of trainable parameters is 61,706, which is very low, because if I had just took this 32 cross 32 into 3 dimensional vector and do a fully connected layer, in the first layer itself, I could have got like 10,000 parameters. So keep looking into this parameter is low. So this is the end of this notebook. I guess there should be a notebook training MNIST. Yeah. So this one, I'll just run it. Okay. I'll just run it. And then it is loading the data. It is the same old thing that we did earlier, loading the data, printing the data sets. Yeah, this definition is the same as the previous definition. So I'll just run it. So we're copying the weights to see it later. Yeah. So once the network is defined, so first forward pass is defined. Second is defining the loss and optimizer. The loss is the negative log likelihood loss, and the optimizer is Adam here. We're defining that, and then we're training the neural network. So this is the training code. I'll run it now. Hopefully, it will execute sooner. Meanwhile, let me. Yeah, meanwhile, let me do one thing. Let me change the input channel to 3 and run this. And let me also do this to 3 and run this. Yeah, as you can see that there is no change, right? It's just still the same thing, because I'm assuming an input size of 3 and I'm passing input size of 3. So the filter they have generated here is now 3 cross 5 cross 5. If I change the input image dimension to 5 and change your 5, this also shouldn't matter. See, it also still not matter, because the inputs the way I'm if the input size is input channel is say k, the filter that will be generated here will be k into 5 cross 5 here, the kernel size k into 5 cross 5. So yeah, so I guess I can print those filters. I guess print CNN filter in torch. Yeah, I guess model dot features layer weight data clone. Yeah, I can do that. Layer one, the weight and data clone. But I guess like it's just like you can check this, the size will be same. Yeah, we have trained this. You can look into the training code. It's pretty simple. We're just doing a forward pass here, net into input, then calculating the loss, then backward propagation just one line, lost dot backward, and updating the network parameter like w new equal to w old minus something. It is optimizer dot step. So this is the thing. And by doing this, we got this, and we just plotted this loss curve, and we're sort of visualizing the weights now. And so like visualizing the weights, like initial weights of convolution one, and difference of weights in convolution and initial weight convolution to trend weights. So how these weights have changed, you can see. But the main point is that we got a accuracy of around 97.2% using MNIST, and these networks won't be that much be helpful like MNIST, because if you do a ANN also you'll get similar accuracy, but when going to larger images, this type of network will play a crucial role, I guess. Yeah, I guess time is up now. I will start with modifying linear for Cypher 10.
So
Uh,
we have access to these notebooks in lectures in Swayam.
yeah, so there is a GitHub repo corresponding to this corresponding to this DVL. Okay, let me see. DLVC NPTEL. DLVC NPTEL. This one. I'm putting it in the chat.
Yeah, that would be helpful.
Take into that, and the YouTube channel is what happened? Hmm. This is a YouTube channel where I'll be uploading all these things. Uh, you can find all this recorded lecture there. So you just keep a note of this chat.
Yeah, I did subscribe to the channel. It's pretty helpful. Yeah, thank you. Thank you for the class. I mean, upcoming session. See you next week. Thank you. Have a
Thank
good
you. Bye.